Hello friends, in this video we shall discuss phase sequence. So often in the analysis of three-phase system we come across this term phase sequence, and this term phase sequence can also be called as the phase order. It can also be called as the phase order. Now the phase sequence or the phase order is the order in which the voltages in the three phases or three coils reach their maximum positive values is called the phase sequence or the phase order. Now instead of maximum positive values, you can also go for any other instantaneous value that can be used to determine the phase sequence. Okay, now let us see how can we obtain the three phase voltages in a elementary alternator. So let us see here it is we are having a elementary three phase alternator. It has three identical windings, or you can say coils: coil A, coil B and coil C, which are displaced 120 degrees electrical from each other and rotating in anti-clockwise direction. This is the direction, anti-clockwise. So they are rotating in the anti-clockwise direction with the angular velocity omega. Okay, let us take an elementary three-phase alternator which is having three coils: coil A, coil B, coil C, and these are displaced by 120 degrees electrical and they are rotating in anti-clockwise direction with the angular velocity omega in the two-pole field, as we are having two poles, north and south, so they are rotating in the two-pole field. Now note that the corresponding terminals A1, B1, C1 are 120 degree apart. Likewise, the terminals A2, B2 and C2 are also 120 electrical degrees apart. They are 120 electrical degrees apart. And now since the three coils are identical and have the same angular velocity omega, okay, the EMFs induced in them will be of the same magnitude and the frequency. Okay, that is according to the Faraday's law. The induced EMF in all the three coils will be of same magnitude and frequency. However, the three EMFs, that is the EMFs induced in the coil A, coil B and coil C, will be displaced from one another by 120 degrees, and you can note the EMF in the coil B will be 120 degree behind that of coil A, and the EMF in the coil C will be 240 degree behind that of coil A. Okay, 240 degree behind that of coil A, and you can see from the wave diagram of the three phase voltages here. So this is the wave diagram where you can see the coil A or the phase A is obtaining the maximum positive value first, and the coil B is obtaining its maximum value next, and later it is followed by the phase C. Okay, and each EMF are displaced by 120 degrees from each other. Okay, so phase B and phase A are displaced by 120 degrees, phase C and phase B are displaced by 120 degrees, whereas phase C and phase A, so this is phase C and this is phase A, they will be also displaced by 120 degrees, but here it is in the minus 120 degrees, that is minus 120 electrical degrees apart. Okay, that is we call minus 120 degrees, or you can say simply it is 240 degree between, that is the angle between the phase A and the phase C. So here what you can witness is, if I write the voltage expressions, that is E A1 A2 will be equal to simply Em sine omega t from the elementary three-phase alternator, where the EMF in the coil A1 A2 will be simply Em sine omega t, and whereas the EMF in the coil B1 B2 will be Em sine omega t minus 120 degrees. Okay, similarly C1 C2 will be Em sine omega t minus 240 degrees. Okay, this is how the voltage expressions will be. Now the phase sequence will be generally determined by the direction of alternator, that is direction of rotation of alternator, the phase sequence is determined. So here you can see in the anti-clockwise direction, first you will be having the coil A1, A2, and next after 120 degrees you will be having coil B1, B2, and after 240 degrees you will be having the coil C1, C2. So basically you can see here it is the angle between the electrical degree between the coil A and coil B will be 120 degrees, and the electrical degree between the coil C and coil A will be 240 degree. Okay, there is a spatial distribution of the windings or the coils between the two poles north and south. Okay, so here the phase sequence is generally determined by the direction of rotation of alternator, and the three coils A, B, C are producing the voltages that are displaced 120 degree apart from each other, and whereas the voltage in coil A attains maximum value first and later on B and later on C, and hence you can say the phase sequence here it is nothing but A, B and C, where A is attaining maximum value first, maximum positive value first, then B, then C. Okay, now if the direction of rotation of this alternator is changed, that is if you make this as clockwise, then the order in which the three phase attain their maximum positive values would be A, C and B, because when you go for the clockwise direction, first you will be having the coil A1, A2, and this will be followed by the coil, this is 120 degrees, the coil you will be having C1, C2, and from here you will be having the coil B1, B2, that is now the coil B1, B2 will be, sorry, it is 240 degrees from the coil A1, A2, that is from the coil A, the coil B is 240 degrees, there is electrical degrees, and from the coil A, the coil C is 120 degrees. So the phase sequence it will be in this fashion A, C, B, and you can see since the alternator can be rotated in either clockwise or anti-clockwise direction, there can be only two possible phase sequences. Okay, that is the two possible phase sequences are ABC and other one is the ACB. And if you see the application of this phase sequence, the phase sequence example you can say in a three-phase induction motor, the phase sequence of the supply determines whether the motor runs in clockwise or anti-clockwise direction. So the phase sequence can also be reversed by changing any of the two, that is any two of the three lines. Okay, by changing any two of the three lines, let me say we are having, otherwise I will draw the diagram here for the, let me say this is R, okay, this is Y, this is B, or you can also indicate this as A, this is B, that is the coil A, this is coil B, coil C. Okay, so here let me say they are rotating in the clockwise direction, so the phase sequence will be A, B and C. Okay, now if any two of the three lines means supply, when you connect it to a three-phase load, let me say this is R, Y, B, and if you change any two of the three lines, so you can interchange any of the phases here, then the direction will be simply this is R, and this will be B, and this will be C. Okay, now you can see the new phase R, B, Y. Okay, so these two phases we can see by convention the sequence R, Y, B is taken as positive, and R, B, Y is taken as negative. So thereby we are having only two phase sequence. One is the positive phase sequence and another one is the negative phase sequence, and these phase sequence are nothing but the rotation of the alternator in clockwise and anti-clockwise directions. Okay, as we are having only two directions, there will be the possibility of only two phase sequences. Okay, this may be your Viva questions where we are having only two phase sequences. Okay, and now let us come to the question: how will you determine the phase sequence? Okay, how will you determine the phase sequence of a three-phase line? Okay, let me say I am having a three-phase line R, Y and B. Okay, we are having the three phase sequences R, Y and B. Now, you, when you initially give the supply to a three-phase motor and you do not know the phase sequence in which the connections has to be applied, then how will you determine the phase sequence of the three-phase line without neutral connected? So there is no neutral here, but we are having only three phases and we have to determine the phase sequence of this three-phase line. So the phase sequence of the three-phase line can be easily determined by a simple way by using two 60-watt incandescent lamps and by using a capacitor. Okay, so by using two 60-watt incandescent lamps and by using a capacitor, you can determine the phase sequence. Now if we connect this star load of lamps and capacitor to a three-phase line, so they are connected in a star fashion. Okay, they are connected in a star fashion. So how will you determine the phase sequence? The phase sequence can be determined when we connect the star load and the capacitor in a star sequence, or when they are star connected, one lamp will always burns brighter than the other. One lamp will always burns brighter than the other, and the sequence will be in the fashion that is, first we are having bright lamp, then the dim lamp and then the capacitor. So this is how the sequence is taken. So bright lamp, dim lamp, capacitor, and that is R, Y and B. So this is how the sequence is determined by using simply two 60-watt incandescent lamps and a capacitor, and the sequence can be determined in the fashion the brighter lamp, the dim lamp and the capacitor, because in one of the phases you will be witnessing one lamp will glow brighter than the other lamp, and the brighter lamp will be taken as the first sequence, followed by the dim lamp and followed by the capacitor, and this is how the phase sequence is determined, where the R phase will burn brighter with the Y phase with the dim lamp and the B phase with the capacitor. So the phase sequence is R, Y, B, and the naming of the phases generally they can be numbered. Phases they can be numbered or they can be lettered, but in practice the three phases or windings are given after the three natural colors red, yellow and blue, and the phase sequence, as we say, it is R, Y, B. That is for the positive phase sequence, and for the negative phase sequence it is R, B, Y. So this is all about the phase sequence. I hope you understood well. Thank you.